Hello class, and welcome to part 3 of the origin of modern astronomy. So in this lesson, we will go back in time to that period right after Nicholas Copernicus had proposed the heliocentric model of the universe. So come with me and let's go back in time during that period right after Nicholas Copernicus had proposed the sun-centered model of the universe. So beam me up now, Scotty. Alright, energize. Hello class, and welcome to part 3 of the origin of modern astronomy. So in this lesson, we will go back in time during that period right after Nicholas Copernicus had proposed the heliocentric model of the universe. Now, this geocentric model of Ptolemy was accepted for several centuries until an astronomer by the name of Nicholas Copernicus came up with another model of the solar system of the universe by placing the sun at the center. Copernicus formulated a model of the universe that placed the sun at the center of the universe rather than the earth at the center. Okay, so we know this now as the heliocentric model of the universe. So Copernicus had placed the sun rather than the earth at the center of the universe. So we call this the heliocentric model. Helio meaning sun, sun-centered model of the universe. Now, using this heliocentric model, Nicholas Copernicus was able to solve the problem of retrograde motion of the planet, especially that of Mars. Now, according to Nicholas Copernicus, retrograde motion occurs roughly when a faster moving planet catches up to and passes a slower moving planet. Now everybody, I want you to zoom in on this animated illustration. Now the blue dot represents Earth and the red dot represents Mars. Now we know for a fact that the Earth moves around the Sun faster as compared to Mars, as Mars is a slower moving planet. So as the Earth passes Mars, we see here from our perspective here on Earth that Mars moves in a retrograde motion with respect to the background of stars. Fascinating, isn't it? So that's how Nicholas Copernicus explained retrograde motion of the planets, especially that of Mars, using his heliocentric model. So retrograde motion, according to Nicholas Copernicus, occurs when a faster moving planet like planet Earth catches up to and passes a slower moving planet like Mars. So we see here from our perspective here on Earth that Mars moves in a retrograde motion. Now you will notice in the explanation provided by Nicholas Copernicus in explaining the retrograde motion of the planet, especially that of Mars, he eliminated the use of epicycles. He never mentioned anything about epicycles in his heliocentric model. So in a way, Nicholas Copernicus had contradicted Claudius Ptolemy by eliminating epicycles. Now we know before that Claudius Ptolemy had introduced epicycles in explaining the retrograde motion of the planet, especially that of Mars, in his geocentric model. So Nicholas Copernicus, using the heliocentric model, helped explain the retrograde motion of the planet, especially that of Mars. And he contradicted, by eliminating epicycles, he contradicted Claudius Ptolemy. Okay? Alright, and Nicholas Copernicus came up with his book entitled On the Revolutions of the Heavenly Spheres. And by eliminating the use of epicycles in his model and contradicting Claudius Ptolemy, the church did eventually ban the book in 1616. Now that was really a very interesting story of Nicholas Copernicus. So his book On the Revolution of the Heavenly Spheres, written in 1532, was banned by the Catholic Church. Again, because he eliminated epicycles in his model and he placed the sun at the center of the universe. So this was his book On the Revolution of the Heavenly Spheres. And in this book, he placed the sun at the center of the universe. And he also explained the retrograde motions of the planet, especially that of Mars. Now, what's wrong with the heliocentric model was that Nicholas Copernicus failed to compile astronomical data that would support his model. Now, this guy by the name of Tycho Brahe did just that. Tycho Brahe was able to compile astronomical data. Now, Tycho Brahe was a Danish astronomer known for developing astronomical instruments that would measure the positions of stars. Okay, this was his observatory, and Tycho Brahe was really famous for his astronomical instruments. He built and constructed huge instruments like this quadrant. So this quadrant was used to measure the angular distances of stars, much like the sextant used by seafarers and the Navy. Alright, so that's the quadrant. Alright, so here is again the quadrant that was used to measure the angular distances of stars, much like the sextant of today. Alright, so Tycho Brahe was really famous for these huge astronomical instruments that would aid with his naked eye observations. Now, his observations, the most accurate possible before the invention of the telescope, included a comprehensive study of the solar system, especially Mars, and accurate positions of more than 777 fixed stars. Tycho Brahe was one of the greatest of the naked eye astronomers. And Tycho Brahe made calculations of the position of Mars in 1576. Fascinating, isn't it? Now, what's interesting about Tycho Brahe was that Tycho Brahe also came up with his model of the solar system. Alright, so everybody, I want you now to take a look at this diagram of the model made by Tycho Brahe. Okay, so you will notice that in his model, or the so-called Tychonic model, he placed the Earth at the center of the universe, much like the geocentric model. So the Earth is at the center, the Moon revolves around the Earth, and also the Sun. If you will notice, the Sun also revolves around the Earth. But everybody, look at the Sun. So all the planets, okay, Mercury, Venus, Mars, Jupiter, and Saturn, they all revolve around the Sun, much like the heliocentric model of Nicholas Copernicus. Alright, so this was the so-called Tychonic model of the solar system. So it is like the combination of the geocentric and heliocentric models. So in this Tychonic model, the Earth is at the center. The Moon and the Sun revolves around the Earth. But the 5 visible planets, they all revolve around the Sun. So here is a combination of the geocentric model and the heliocentric model. So this was the model made by Tycho Brahe, the so-called Tychonic model of the universe. So before we move on, let's watch this fascinating video about Tycho Brahe. So let's watch this.
How do you imagine the life of a scientist? Boring and monotonous, spending endless hours in the lab with no social interaction? Maybe for some, but not Tycho Brahe. The 16th century scholar who accurately predicted planetary motion and catalogued hundreds of stars before the telescope had been invented also had a cosmic-sized personal life. Tycho Brahe was born in 1546 to Danish nobles, but at age 2 was kidnapped to be raised by his uncle instead. His parents didn't seem to mind. Tycho was supposed to have a career in law, but after witnessing a solar eclipse at 13, he began spending more time with mathematics and science professors, who taught him the art of celestial observation. By the time Tycho's uncle sent him off to Germany a few years later, he had lost interest in his law studies, instead reading astronomy books, improving his instruments, and taking careful notes of the night skies. It wasn't long before his own measurements were more accurate than those in his books. While in Germany, Tycho got into a bit of an argument with another student at a party over a mathematical formula, resulting in a sword duel and Tycho losing a good-sized chunk of his nose. After that, he was said to have worn a realistic prosthetic of gold and silver that he would glue onto his face. Fortunately, Tycho didn't need his nose to continue his astronomical work. He kept studying the night sky and creating all sorts of instruments, including a building-sized quadrant for measuring the angles of stars. After months of careful observation, Tycho discovered a new star in the constellation Cassiopeia. The publication of this discovery granted him rock star status and offers of scientific positions all over Europe. Wanting to keep him at home, the King of Denmark offered to give Tycho his own personal island with a state-of-the-art observatory. Called Uraniborg and costing about 1% of Denmark's entire budget, this observatory was more of a castle, containing formal gardens, rooms for family, staff, and visiting royalty, and an underground section just for all the giant instruments. Tycho also built a paper mill and printing press for publishing his papers, and a lab for studying alchemy. And since no castle would be complete without entertainment, Tycho employed a clairvoyant dwarf named Jep as court jester. Tycho lived on his island, studying and partying for about 20 years. But after falling out with the new Danish king, he took up an invitation from the Holy Roman Emperor to become the official imperial astronomer in Prague. There he met another famous astronomer, Johannes Kepler, who became his assistant. While Kepler's work interested him, Tycho was protective of his data, and the two often got into heated arguments. In 1601, Tycho attended a formal banquet where he drank quite a lot, but was too polite to leave the table to relieve himself, deciding to tough it out instead. This proved to be a bad idea, as he quickly developed a bladder infection and died a few days later. But over 400 years after his death, Tycho still had a few surprises up his sleeve. When his body was exhumed and studied in 2010, the legendary gold and silver nose was nowhere to be found, with chemical traces suggesting that he wore a more casual brass nose instead. Tycho's mustache hair was also found to contain unusually high levels of toxic mercury. Was it from a medicine used to treat his bladder infection? A residue from his alchemy experiments? Or did his quarrelsome co-worker Johannes Kepler poison him to acquire his data? We may never know. But the next time you think scientists lead boring lives, dig a little deeper. A fascinating story may be just beyond the tip of your nose.
Now, even though Tycho Brahe was really good in his naked eye observations, he was not good in math. So he needed some mathematical assistance to aid in his calculations. So he hired someone by the name of Johannes Kepler. But Tycho Brahe had some temperamental issues. So Kepler and Brahe did not get along really well. Okay? So Tycho Brahe apparently mistrusted Kepler, fearing that his bright young assistant might eclipse him as the premier astronomer of his day. Kasi magaling si Johannes Kepler sa math. So medyo na insecure si Tycho Brahe. Alright? So he mistrusted Kepler, fearing that his bright young assistant, kasi matalino tong si Kepler, might eclipse him, baka masapawan siya as the premier astronomer of his day. So he let Kepler see only part of his voluminous data. Hindi niya masyadong pinagkatiwalaan si Johannes Kepler. Okay? So that was Johannes Kepler and Tycho Brahe.
Please, Spock, do me a favor, and don't say it's fascinating. No. But it is interesting.
Now, as you could see, the working relationship between Tycho Brahe and Johannes Kepler was not really good. And when Tycho Brahe died, Kepler was really joyous. Why? Because Kepler got access to Brahe's voluminous astronomical data. So when Tycho Brahe died, Kepler got access to Brahe's astronomical data, and using his brilliance in mathematics, Kepler formulated the laws of planetary motion using the data provided by Tycho Brahe. So that was really interesting. So when Tycho Brahe died, Kepler used Brahe's data to develop the three laws of planetary motion that explained the movement of the planets. So at this point, let us now go into the details of the laws of planetary motion by Johannes Kepler. Okay, this is the first law. Now, according to Kepler's first law, all planets move about the sun in elliptical orbits, having the sun as one of the foci. So, according to Johannes Kepler, a planet moves not in perfect circles as mentioned by Nicholas Copernicus, but a planet moves in an elliptical path or an oval-shaped orbit, as you could see in this animated illustration. So all the planets, including our Earth, all the planets, they move around the sun in an elliptical path. So that was Kepler's first law. Now, because a planet moves around the sun in an elliptical orbit as mentioned in the first law, there are times wherein the planet is closest to the sun, and there are times wherein the planet is farthest from the sun. So, the point wherein the planet is closest to the sun is called the perihelion, and that point wherein the planet is farthest from the sun is the aphelion. Now, everybody look at the speed at which the planet moves around the sun. As it approaches the perihelion, the planet speeds up. And when the planet approaches the aphelion, it slows down. Alright? So, a planet moves most rapidly when it is nearest the sun or the perihelion. And a planet moves slowly when it is farthest from the sun or the aphelion. And this was the basis of Kepler's second law of planetary motion. Kepler's second law of planetary motion describes the speed of a planet traveling in an elliptical orbit around the sun. Okay? So the speed of the planet increases as it nears the sun, and it decreases as it recedes from the sun. Alright? Okay, so as you could see here in this animated illustration, so when the planet approaches the perihelion, the planet speeds up, and when the planet approaches the aphelion, the planet slows down. Okay, so that's Kepler's second law of planetary motion. Now, what about Kepler's third law of planetary motion? Now, according to Kepler's third law, how long a planet takes to go around the sun is related to the planet's mean distance from the sun. Now, everybody, I want you now to take a look at this animated illustration. Now, the yellow dot represents the sun, who is at the center of the universe. The blue dot represents planet Earth, while the green dot represents the red planet Mars. Now, we know for a fact that the Earth takes about 365 days to complete one revolution around the sun, while Mars takes about 686 days to complete one revolution around the sun. Now, knowing that Mars is farther from the sun as compared to Earth, Johannes Kepler concluded that the farther the planet is from the sun, the slower is its orbital speed, as you could see in the planet Mars. Mars takes longer for it to complete one revolution around the sun as compared to Earth. Alright? Okay, so let's take a look at the planet Jupiter. Now, here is the mathematical application of Kepler's third law. Okay, in calculating the revolution of Jupiter around the sun. Now, based from this mathematical calculation of the revolution of Jupiter around the sun, Jupiter takes about 11.8 years to complete one revolution around the sun. Okay, knowing that Jupiter is farther from the sun as compared to Mars. Mars takes about 686 days to complete one revolution. While Jupiter is farther from the sun as compared to Mars, Jupiter takes about 11.8 years to orbit the sun. Okay, so that's quite fascinating. Now, everybody, let's take a look at Venus. Now, Venus takes about 224 days to complete one full circle around the Sun, knowing that Venus is closer to the Sun as compared to Earth. The Earth takes about 365 days to complete one revolution around the Sun. Alright, so that's Kepler's third law. The farther the planet is from the Sun, the slower is the orbital speed of the planet. Alright, okay, so that's Kepler's third law of planetary motion. So again, let's take a look at Jupiter in this animated illustration. So Jupiter, being farther from the Sun as compared to the inner planets, Jupiter takes about 11.8 years to complete one revolution around the Sun. Okay, so the farther the planet is from the Sun, the slower is its orbital speed. Okay, so that's quite fascinating, isn't it? Alright, but the problem with Johannes Kepler is that he was able to describe the movements of the planets, but he cannot explain the reason for such behavior of the planets around the Sun. So that explanation will be provided later on by Isaac Newton. Okay, class. So the life of Johannes Kepler was really interesting indeed and fascinating. So let's watch this video about Johannes Kepler. Okay, so let's watch this.
Johannes Kepler was born in Germany in 1571. He was sent to the Protestant seminary school in the provincial town of Maulbronn to be educated for the clergy. It was a strict, disciplined life, up before dawn to begin a long day of prayer and study. This was the age of the Reformation. Maulbronn was a kind of educational and ideological boot camp, training young Protestants in the use of theological weaponry against the fortress of Roman Catholicism.
Denn ich befehle mich, meinen Leib und Seele, alles in deine Hände.
There was little reassurance or comfort here for a sensitive boy like Kepler. He was intelligent, and he knew it. That, together with his stubbornness and his fierce independence, served to isolate him from the other boys. Kepler made few friends in his 2 years at Maulbronn. So he kept to himself, withdrawn into the world of his own thoughts, which were often concerned with his imagined unworthiness in the eyes of God. He despaired of ever attaining salvation. But God to him was more than punishment. God was also the creative power of the universe. And the young Kepler's curiosity about God was even greater than his fear. He wanted to know God's plan for the world. He wanted to read the mind of God. This was his obsession. It was to inspire all his great achievements. It was to take him and Europe out of the cloister of medieval thought. In places like Maulbronn, the faint echoes of the genius of antiquity still reverberated. Here, in addition to theology, Kepler was exposed to Greek and Latin, music and mathematics. And it was in geometry that he thought he glimpsed the image of perfection. He was later to write Geometry existed before the creation. It is co-eternal with the mind of God. Geometry provided God with a model for the creation. Geometry is God Himself. But the real world of Kepler's time was far from perfect. It was haunted by fear, pestilence, famine, and war. Superstition was a natural refuge for people who were powerless. Only one thing seemed certain: the stars themselves. It was remembered that in ancient times the astrologer Ptolemy and the sage Pythagoras had taught that the heavens were harmonious and changeless. And Ptolemy had said that the motions of the planets through the stars of the zodiac were portents of events here below. Was it the influence of Mars and Venus that made his father a brutal man, a mercenary who had abandoned him? Did an unfortunate conjunction of planets in an adverse sign make his mother a mischievous and quarrelsome woman? If such things were fated by the stars, then perhaps there were hidden patterns underlying the unpredictable chaos of daily life. Patterns as constant as the stars. But how could you discover them? Where would you begin? If the world and everything in it was crafted by God, then shouldn't you begin with a careful study of physical reality? Was not all of creation an expression of the harmonies in the mind of God? The book of nature had waited 1,500 years for a reader. In 1589, Kepler left Malbrunn to continue his studies at the great university in Tubingen. It was a liberation to find himself amidst the most vital intellectual currents of the time. One of his teachers revealed to him the revolutionary ideas of Copernicus. Kepler relished this urbane, scholarly community. Here, his genius was recognized at last. Kepler was not to be ordained after Tubingen. Instead, to his great surprise, he found himself summoned to Gratz in Austria to become a teacher of high school mathematics. Kepler was not a very good teacher. The first year in Gratz's mathematics class had only a handful of students. The second year, none. He mumbled, he digressed, he was at times utterly incomprehensible. He was distracted by an incessant clamor of speculations and associations that ran through his head. And one pleasant summer afternoon, with his students longing for the end of the lecture, he was visited by a revelation that was to alter radically the future course of astronomy and the world. There were only 6 planets known in his time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. For some time, Kepler had been wondering, why only 6 planets? Why not 20 planets or 100? And why this particular spacing between their orbits? No one had ever asked such questions before. In the course of a lecture on astrology, Kepler inscribed within the circle of the zodiac a triangle with 3 equal sides. He then noticed, quite by accident, that a smaller circle inscribed within the triangle bore the same relationship to the outer circle as did the orbit of Jupiter to the orbit of Saturn. Could a similar geometry relate the orbits of the other planets? Now Kepler remembered the perfect solids of Pythagoras. Of all the possible three-dimensional shapes, there were 5, and only 5, whose sides were regular polygons. He believed that the two numbers were connected, that the reason there were only 6 planets was that there were only 5 regular solids. In these perfect solids, nested one within the other, he believed he had discovered the invisible supports for the spheres of the 6 planets. And this connection between geometry and astronomy could, he thought, admit only one explanation: the hand of God, mathematician. The intense pleasure I received from this discovery can never be told in words, he said. Now I no longer became weary at work. Days and nights I passed in mathematical labors until I could see whether my hypothesis would agree with the orbits of Copernicus or if my joy would vanish into thin air. But no matter how hard he tried, the perfect solids and the planetary orbits did not agree with each other very well. Why didn't it work? Because unfortunately, it was wrong. The true orbital sizes of the planets, we now know, have absolutely nothing to do with the 5 perfect solids, as the later discovery of Uranus, Neptune, and Pluto shows. But Kepler spent the rest of his life pursuing this geometrical phantasm. He couldn't abandon it, and he couldn't make it work. His frustration must have been enormous. Finally, he decided that it must be the long-accepted planetary observations that were inaccurate, and not his model of the nested solids. There was only one man in the world who had access to more precise observations. That man was Tycho Brahe, who, as chance would have it, had recently written Kepler to come and join him. Kepler was reluctant at first, but he had no choice. In 1598, a wave of oppression enveloped Gratz. It was spearheaded by the local archduke, who vowed to restore the Catholic faith to the province and, in his own words, would rather make a desert of the country than rule over heretics. Kepler's school was closed, people were forbidden to worship or to sing hymns or to own books of a heretical nature. Those who refused to embrace Catholicism were fined 10% of their assets and exiled from the country on pain of death. Kepler chose exile. Hypocrisy I have never learned. I am in earnest about faith. I do not play with it. For Kepler, it was only the first in a series of exiles forced upon him by religious fanatics. Now he decided to accept Tycho Brahe's open invitation. Brahe, a wealthy Danish nobleman, lived in great splendor and had recently been appointed imperial mathematician at Prague. Kepler left Gratz with his wife and stepdaughter and set out on the difficult journey. Kepler's wife was not a happy woman. She was chronically ill and had recently lost 2 young children. The marriage itself was no comfort, She had no understanding of her husband's work and regarded his profession with contempt. Kepler was married to his work, and every tedious mile was bringing him closer to the great Tycho Brahe, whose observations, he devoutly hoped, would confirm his theory. Kepler envisioned Tycho's domain as a sanctuary from the evils of the time. He aspired to be a worthy colleague to the illustrious Tycho, who for 35 years had been immersed in exact measurements of a clockwork universe, ordered and precise. But Tycho's court was not at all what Kepler had expected. Tycho himself was a flamboyant figure, adorned with a gold nose. The original had been lost in a student duel fought over who is the superior mathematician. And he maintained a circus-like entourage of assistants, distant relatives, and assorted hangers-on. Kepler had no use for the endless revelry. He was impatient to see Tycho's data, but Tycho would give him only a few scraps at a time. Tycho, he said, gave me no opportunity to share in his studies. He would only, in the course of a meal and in between other matters, mention, as if in passing, today the figure of the apogee of one planet, tomorrow the nodes of another. Kepler was ill-suited for such games, and the general climate of intrigue offended his sense of propriety. Their cruel mockery of the pious and scholarly Kepler depressed and saddened him. My opinion of Tycho is this. He's superlatively rich, but knows not how to make proper use of it. Tycho possesses the best observations. He also has collaborators. He lacks only the architect who would put all this to use. Tycho was unable to turn his observations into a coherent theory of the solar system. He knew he needed the brilliant Kepler's help. But simply to hand over his life's work to a potential rival, that was unthinkable. Tycho was the greatest observational genius of the age, and Kepler the greatest theoretician. Either man alone could not achieve the synthesis which both felt was now possible. The birth of modern science, which is the fusion of observation and theory, teetered on the precipice of their mutual distrust. The two repeatedly quarreled and were reconciled, until, a few months later, Tycho died of his habitual overindulgence in food and wine. Kepler wrote to a friend, on the last night of Tycho's gentle delirium, he repeated over and over again these words, like someone composing a poem. Let me not seem to have lived in vain. Let me not seem to have lived in vain. And he did not. Eventually, after Tycho's death, Kepler contrived to extract the observations from Tycho's reluctant family, observations of the apparent motion of Mars through the constellations obtained over a period of many years. The data from the last few decades before the invention of the telescope were by far the most precise ever obtained up to that time. Kepler worked with a kind of passionate intensity to understand Tycho's observations. What real motions of the Earth and Mars about the Sun could explain to the precision of measurement the apparent motion as seen from the Earth of Mars in the sky. And why Mars? Because Tycho had told Kepler that the apparent motion of Mars was the most difficult to reconcile with a circular orbit. After years of calculation, he believed that he had found the correct values for a Martian circular orbit which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and of course, 90 degrees from horizon to zenith. So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom because 2 further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the Sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the Sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the Sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the Sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the Sun, the area is long and thin. When the planet is close to the Sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the Sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times. Kepler's first 2 laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys, as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question, what makes the planets go? Kepler's third, or harmonic law, states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power, of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law. Kepler was the first person in the history of the human species to understand correctly and quantitatively how the planets move, how the solar system works.